We're going to try and record it for them. Okie dokes. So, topic we have today is all about negative emissions. Can negative emissions from bioenergy systems become reality? That's what we're going to talk about. Why is this important? Well, it might surprise you just how much we're relying on this. Over 100 of 116 scenarios that limit us to 2 degrees C depend on biomass to energy with carbon capture and storage. Once we start looking at 1.5 degrees, that's what we think might be tolerable and what we're aiming for, then 3 of the 4 pathways in the IPCC report rely on this. In the UK, that means that we are looking at delivering 20 to 70 million tonnes per annum of negative emissions. But very critically, there's a business case for this. We believe that this will actually reduce the cost of meeting the 2050 emissions target. So this is something that is embedded into our plans because of where we are. And that's where we are. That in order, these are 4 different pathways that have us meeting our 2050 targets. And the bit in yellow is the BECCS bit. And what you can see is that the value of doing BECCS is that you can delay when you decarbonise and you don't have to decarbonise as much. Now, arguably, those are not very good reasons for doing BECCS, but that is generally the way it's been argued at the moment. Essentially, it's a get out of jail free card. It avoids us having to do the really difficult stuff, which I think we're all seeing at the moment is looming hard this winter, of actually reducing energy consumption, and not just energy consumption, but reducing the other forms of greenhouse gas emissions that we as a society have. So BECCS gives us a little bit more manoeuvrability on that front. Now, where this all came from first, really, is the world of modelling. Lots of clever people, some of them in this room, who spend a lot of their life modelling energy systems. And when they do that, they reduce everything to a fairly narrow set of parameters. They're not parameters that everyone would recognise. It tends to focus around the energy output, the cost, the carbon intensity. So some of the things that we as engineers might think of as important around flexibility, around the practicality of building things, around the environmental impact, don't get included in these models. It's just interested in how can I get rid of CO2 while maintaining my energy demand at the minimum cost. And if you look here at 4 categories, let's call them, of the sort of things that go into this model, you can see why BECCS is so attractive. We started with fossil fuel-based power generation. That gives us energy. That's what we want. It unfortunately also carries with it CO2 emissions, but it's pretty low cost until this year. And therefore we have, used that a lot in the past. Renewables, when it first came in, was very high cost, but it does give us energy, which we need as a society. And theoretically, gives no CO2 emissions, although in practice, if we draw the boundaries appropriately, we all know that it does, but they're lower CO2 emissions. So these are things that we want. We're attracted by the fact that the renewables will give us low CO2 and energy output. But we rapidly realise, and you will have seen this in the previous graphs, that renewables on their own are not enough. We need to actually remove greenhouse gases from atmosphere. And one of the big challenges with doing that is that many of the methods out there, such as direct air capture, actually require energy. So we have this sort of circle. You've got to put energy in order to get CO2 locked away. So yes, greenhouse gas removal projects can give you negative CO2 emissions, but you pay. You pay in terms of cost, which is quite high per tonne of CO2 removed, and you also pay in terms of the energy consumption. From an energy system modeller's perspective, BECCS is quite different. Because as I've highlighted in green, it combines the positive attributes of the previous. It gives you energy and it gives you negative CO2 emissions. Or so they conflate it in their world, where they draw scope around certain things that will ensure that that is how we characterize these technologies. So effectively, we have a unicorn. We have something that can give us everything we need, but actually no one knows that it can work, and no one has ever proven it. I'm being slightly facetious. We have proven different elements of this, because this is what the full BECCS chain actually looks like. We have land use associated with our production of the material, and then we harvest it. There's a pre-treatment process. We convert this to get our energy from it, and then we store the CO2. The bits in blue are our CO2 uptake. So that is all around the biomass production on the land that we have. And that's got to be balanced by all those bits in red. So the red are all the emissions that we have at different points in time. Oh, I didn't realize this was going to do this. This is what happens when you borrow other people's slides. But there you go. So let me just go back, actually. Okay, so this is all fine in theory. So we've moved on from the world of the energy system modelers and the unicorns, where they say, let's put a number in the spreadsheet that says that I get negative CO2 emissions and I get it at a wonderful price and it gives me energy as well. And obviously, the model will pick that every time. And that's how we end up with that curve that says, hey, we need loads of BECCS and we need it tomorrow. We've moved on from that and we've started to dissect what the individual bits of this are. What we've been doing in Supergen and in Aston over the last year or two is looking a bit more at what's behind that. So we've been looking at some specific studies, and this is particularly drawing on work that Miriam, who's sitting over there, has done with Alberto, whom I don't, here he is at the front, excellent. You see a lot of your slides coming up here, Alberto. Mm-hmm. And this is work that was done across a number of different projects, but looking at the engineering detail of whether we can take those high-level numbers, the dancing unicorn, and actually turn it into something that's tangible, that we can actually build. When we look at the detail of the system and what it actually involves, is it still viable? And Alberto will tell you, he has spent many painful hours with me sitting going at him, but why would anybody build it like that? And why would you do this? And the systems that he has modelled are very practical, very sensible, very realistic. They are not the same as what has been put into previous versions of these energy system models with the high-level numbers. So these are two examples that he's been working on over the last year or so. A small-scale facility, KSA, of CHP plant, which is fueled with wheat straw, and the one on the right, the hydrogen production using forest residue. Now, it is gone 5 o'clock in the evening, and I am aware that I stand between you and dinner. So you will be relieved to hear, not going to show all of the results of the very clever Aspen modelling and the techno-economics and LCA that Alberto has done. But instead, here's the high-level output. And you will be pleased to see that what he has done is confirm that we can actually, when we go through the engineering detail and account for everything and add it all up and look at the supply chain and say, hang on, what about the carbon that was embodied? What about the forest? What about the soil carbon? We can take all that into account and we can still show that this actually will deliver negative emissions. So this is possible. And the negative emissions he has calculated per facility. And if you look at the reference on the bottom there, you can follow this up. And what you see is that you need an awful lot of these to get even anywhere near what the UK's target is. So the CHP facility on there, to reach just the 20 megatons, which you may remember was at the lower end of the range that the UK is ambitious for, you would need 64 of those facilities, and the one on the right, a mere 7,900 of those scattered around the country. That's dead easy, isn't it? So I think we need a reality check here, in that there are different ways of doing BECCS. They have different performance parameters. I think this gets glossed over way too much. We use arbitrary numbers. And the reality in terms of consequences are that you actually are using your resource to deliver different things. And we are dealing here with a huge ambition in terms of being able to plan, design, consent, build, operate, and deliver this sort of scale of activity moving forward. And this is what we currently think we're going to be doing by 2050. Now, again, I'm being slightly facetious here in that there are other options. One could go for the very mega-sized option that probably would require, I would argue, international collaboration at a sort of DRAX type scale or larger. And you could do that with an international BECCS hub. And we did look at this a few years ago with the Committee on Climate Change and came to the conclusion that the numbers around that were so uncertain that we daren't publish them. So that is possible, but we are not, I don't believe, at the point where we can really be thinking about putting sensible numbers that would allow us to include that in our targets. And that's because of this. Because at the moment, worldwide, there are 6 functional facilities. 1 large-scale one for bioethanol. There are 2 pilot plants in the UK. And to give you an idea of the sort of scale-up that we need here, that means that globally, we're currently sequestering about 1.5 million tonnes per annum. And we need to be 1,300 times higher than that by the time we get to 2050. So that is the level of ambition that we're talking about. The UK, we've got 2 pilot plants. 20 to 70 megatons per annum is all that we need. So we're only looking at a factor of 100 scale up in the UK. So it gives you an idea of how far we need to go. And I think the thing that bothers me most about this actually isn't the resource. A lot of people focus on the resource and its sustainability. What bothers me most is how on earth we're going to build those. How we will have the skills and the capacity to be able to design, deliver, and build these facilities in the UK and globally in the next 30 years. I'm conscious I've got someone sitting in the middle here who works with the ICME very closely and knows that we have real issues with the number of people coming through trained as engineers who are actually capable of handling these facilities. So I think we have a huge looming skills issue. But the other big challenge that we have, and this, yes, for the sharp-eyed among you, this is exactly the same slide as previous with a different title, is we can deliver the negative emissions. The modelling has told us that. We've done the detailed engineering analysis, or Alberto has, and he's worked through that. And we said, yeah, you know what, this all adds up, this can be done. Let's assume we can get over the skills gap and we can actually build these things on the ground. Then we're relying on all these numbers actually balancing out in order to make this net negative. Now, I have a huge amount of time for the argument that, in a sense, these don't need to balance out. In a sense, globally, the planet needs us to take in CO2 from atmosphere, and we as a society need a certain amount of energy. And I sort of think that as long as across the entire Earth, we maintain roughly the same amount of vegetation and forest and stuff as we have now, we're probably not going to go that far wrong in terms of the CO2 balance. What we need to do is to route what we're sequestering to the most appropriate routes where it will save us having to pull the fossil fuel inputs in instead. So I don't get overly excited, actually, about the land issues and the resource issues. The bit that I get worried about is actually the conversion and the sequestration and what we're going to do with that and how we will manage all of that. I don't think there's been enough attention paid to date to the engineering of what we're going to need to remove the CO2 efficiently, to get us to the sort of purity levels that we need to be able to compress and store it, and to be confident that what we're doing with the different options that we have for storage is actually looking at what we want for long enough. So those, for me, are of a slightly bigger concern than the land use issue at the start. And I think the other thing is that there's a huge amount of variability. So I think we're saying here that we can deliver negative emissions, but we've got to have this stuff all in balance. Now, the feedstock has quite a lot of variability, and the carbon balance of the feedstock is absolutely key. We all have heard of the scenarios whereby we are producing, let's say, corn for production of ethanol that is worse than the original fossil fuel type material because of the carbon involved in the production, be it via fertilizer, or whether that is a palm oil which is coming from Indonesia and the land use change is so vast that we're releasing carbon in a way that we're offsetting the good that we're doing. So I think we've all heard those arguments. I think there's enough land on the planet that we can actually work this through. There have been lots of studies done globally looking at different land grades and availability. And I think this can be achieved, but it does depend on location, it does depend on scale, and it depends on how you manage those supply chains. So I think it's something we need to be careful about, but I don't think it's a showstopper. Conversion efficiency is obviously important. That was the next bit in my chain. And as we've shown you with those two examples of Alberto's, that does depend on technology hugely. There's huge variations there and depends on scale. I think one of the things that's really important to realise is that actually removing the CO2 has an energy penalty. And removing more CO2, surprise, surprise, costs more energy. And removing higher quality CO2 also has the same impact. So I don't think that we've adequately thought about the infrastructure needs that we will have, and indeed how we engineer those, who's going to build those and where they're going to go, in order to be able to deliver this completely. It may be achievable, but I haven't seen a strategic plan on that yet. And I think that we need to be really careful, and I'm going to come back to the skills issue again, about the fact that BECCS is going to look different in different parts of the world. It's going to look different even in different locations within the UK. It's going to look different for different feedstocks, different depending on what we're doing with the CO2 and where it's going. And because of that, there's an awful lot of engineering involved here. There's an awful lot of people needing to actually take what worked somewhere, look at how to transpose that, and work out what needs to change, what doesn't need to change, and how we scale up. So that bit does bother me. Let's go back on. You will note 5 points there. I'm going to go through them one by one. Feedstock carbon balance. How do you unlock a low carbon feedstock? The first thing you do is you minimize the inputs. You don't use stuff like corn. Let's be clear on that. Preferably, you don't use soy either, although we can make an argument around partitioning there with meal and oil. But basically, this is work that we did in Manchester many years ago. And the figures I want you to look at are the columns on the left, where you have the global warming potential of fossil fuels. It's the first bar. And then the next bar stacked alongside it are 5 different ways of producing biomass, ranging from ones where we deliberately tried to put as much carbon into the system as possible, to ones where we tried to be really sustainable. And what you note is that they all end up roughly the same. It really doesn't matter. The biomass itself is absorbing carbon from atmosphere, and that is what makes the big difference. So I refuse to get very worked up about lignocellulosic material grown for biomass and the amount of land that uses and the carbon balance embodied within that feedstock. I think it's a different story if we're talking about things like corn, where there's a very high fertilizer input, but for the lignocellulose, I'm pretty relaxed about this. So the first thing you do is you minimize the inputs, and by and large, that can be achieved if we look at lignocellulosic material. The next thing you do is you minimize your land use change. This again was work that we did a long time ago in Manchester. I think this might have been my first ever academic paper, actually. And what we did here was we looked at the difference in payback time for different biofuels, depending on whether you did or didn't have land use change. And lots of people have done much more sophisticated versions of this since, but the numbers are stark. That if you are looking at a soy crop where you do not have land use change, then you get an immediate payback period. But if you have land use change that is coming particularly from forest land, you're looking at over 5,000 years before you pay that back. That is not even remotely helpful for 2050. So I think that we need to be really mindful of land use change. And that brings us to my nemesis here, really, indirect land use change. I will not put this in a slide, but I personally think that indirect land use change is another unicorn. It was a hypothesis made by Searchinger in the US, and he very logically argued that if you have an amount of land and you now say, I'm going to use that for biomass, then you must have displaced what used to happen there somewhere else. Okay? And therefore, we need to calculate what the carbon consequence of that is. And a lot of people have done a lot of work on this since. There have been a lot of models created, a lot of assumptions made. You can actually get figures for indirect land use change factors for just about any crop you want anywhere in the world. That's very nice, but it's still a hypothesis. The data that we have does not show any significant change in the parts of the world where we have seen land use change actually have an impact. And people say, oh, well, that's because it's indirect, it's further afield. But I think that we are actually lacking an evidence base here around what the real impact of indirect land use change is. I'm not saying it's not there. I just don't see any data. And as a scientist, that really concerns me quite a lot. Because if we're making decisions about what we're planting where, and more importantly, what we're not going to do in order to sort out climate change, then really we need to know this. We need to be looking globally, and frankly, there's enough data out there, we're just not churning it. We need to be looking at all this satellite imaging which we can capture in the regions where we are expanding certain changes of land use, and we need to be looking at whether that is actually mediating changes elsewhere and whether we can quantify what the carbon consequences of that are. Because I get really uncomfortable with some of the ILUC factors that are proposed and are actually even used in legislation sometimes for calculations, because I just don't think we have a credible scientific basis for that. So I put that one out there as something that I think actually is a bit of an open research question. Anyway, something else we can do with our feedstock to minimize the carbon embodied in it is avoid supply chain fossil fuels. Again, work done a very long time ago here, but just showing the difference between drying the material with biomass and drying it with diesel. And what you can see here is that the supply chain actually carries a significant amount of the embodied carbon. Most of it is not in the production. That little purple bit at the bottom, that is the growing of the stuff. It's in the processing, the transport, the drying, the getting it ready for use. So minimizing the supply chain carbon is a really important thing to do. Let's move on from the feedstock. The next thing I said was that the conversion technology had to be efficient. Now, the conversion efficiency varies massively depending on what you're doing, how you're doing it, and how large it is. And I've said this before, removing CO2 costs energy, and removing more CO2 costs more energy. So I think we need to be really, really careful with conversion technologies. And I will look here at Alberto's figures. And what we see here is the CHP plant fueled with the wheat straw. You've got 58 tonnes per hour of biomass coming in on the left there. And what we have going out on the right, in terms of CO2 storage, we've got 68 tonnes per hectare. And these are how the energy consumption in this actually pans out. So for the overall process, the efficiency from biomass to energy is 23%, and we're capturing 78% of the CO2. Now, 23% is pretty poor for most people who are thinking of things as compared to the common thermal plant that we have today. Now, of course, part of the reason for that here is this is CHP, and that is electrical efficiency. So we're not including the heat element of that. But the full paper that you can have a look at does do that. But I'm simply making the point that because we are capturing the CO2, we are using a lot more energy than would be the case in a power plant that was not capturing the CO2, and we need to adequately account for that. And this is the equivalent for the hydrogen system and the hydrogen numbers, and we can see here that this time we're getting 76 kilograms of CO2 per hour being pulled down in this system. We should have an efficiency somewhere. I get to this, yeah. So we've got a higher CO2 capture rate and a slightly higher efficiency, but 27%. So these are not brilliant numbers. There's an awful lot of room for improvement here. And that is why I think one of the things that we need to do is, I've mentioned the skills thing, I've mentioned engineering already. We need to actually build some. We need to get on with building them to find out how they really perform, rather than just playing with models, because only then will we actually learn how to operate them in a way that's efficient and that will give us the returns that we're looking for. I want to come back to the whole system, because the whole system is the unicorn. This is what gives you the negativity. It's if you pull together the land use, the conversion to the energy, and you sequester the CO2. It's combining that pulling, sinking, and energy output that gives you what you're looking for in terms of those parameters for the energy system. But it's a complex system. I argue that actually it has become too complicated. I think that we spend far too much of our time working out how complicated some of these systems are, instead of, as I said earlier, just trying to build one and trying to see how it works and getting our heads around that and actually dealing with this in the real world. But there's another issue with it, which is that as we look down that supply chain, we started with land on the left, and by the time we were on the right, we were sinking CO2, either in some form of underground reservoir or by utilization for production of some long-lived product. And what I think is really significant here is that all of these models and all of the mechanisms that we generally see try to tie this together as a single system, try to draw the scope around the whole thing and reward it on that basis, because that gives us the negativity. But actually, there is no one person who controls all of this. In fact, there is no control over some bits of this. So the land use itself, we can tie ourselves up in knots trying to get figures for the harvesting practices, for the establishment, for the carbon emissions associated with production of biomass in far-flung corners of the world. And I'm often not sure whether that's worth the effort. I'm not sure that the accuracy we gain from that actually really helps us here. So different people are controlling different parts of this system. And arguably the person at the far end, often this comes down to the conversion plant owner. They're the person who will apply for some form of credit for removing CO2 and be required to provide proof of how sustainable their feedstock was and what carbon calculations they've done on the whole supply chain and its life cycle. I'm going to suggest that they are possibly not the best placed people to actually be maximising the carbon that's sequestered in some far-flung forest in another country. That actually the people who are best placed to be managing the feedstock production are the people who are there. The people who manage the forests, the people who own the land, and the people who do that. And that if we try to pull this system from the far end by drawing a big scope around it and saying, altogether it gives us negative emissions, so let's pull that via the people who can do the proper accounting for it, we actually will miss some opportunities. We will miss opportunities around the ability to maximize sustainable feedstock production. We will miss opportunities around the ability to maximize the efficiency of the conversion plant and to do the most sensible thing with the CO2 that we have sequestered. And I think on top of this, we have issues of variability and uncertainty. I was going to use my normal terms, which are variability and variation, but people get annoyed at that. By variability, I mean things where we have made a conscious decision to do something differently that may not be apparent at the far end, but actually has changed the embodied carbon. And therefore we need to know about it and we need to account for it. But variation or uncertainty is something different. It's the fact that we cannot actually know everything that's going on in the world all the time. And because of that, there will inevitably be one field that has a higher yield than another field. And therefore, no matter how carefully you monitor this, you will never know what the true embodied carbon in this system is. And I think we just need to realize that and get on with life. I think that makes effective decision making along this supply chain with these multiple actors with different vested interests really quite challenging. That means that transparency is really key. Transparency is also key for public acceptability of these systems. And frankly, I don't think we have anywhere near enough of this. Yeah, sure, if you look at the renewables obligation figures and go into the website and plow through data, you can find out which countries in the world different bits of biomass came from. But it doesn't give us the level of transparency that we need about the actual production of this stuff to give us confidence that what we're doing is the right thing and that this is actually delivering negative emissions. And then the issue of causality, and this is fraught. Also gets a bit abstract, so I need to be careful here. I have a huge amount of time for the argument, as I said at the start, that there's a certain amount of land on the planet that at the moment is covered in vegetation, and as long as that doesn't change massively, I'm not actually going to get very excited. And if we can keep that roughly in balance and continue to supply our energy needs, I don't see a huge problem. So if we can implement BECCS systems and the forests are still this roughly the same amount of hectares across, let's say, the southeastern US as they are today, and okay, somebody may be doing a bit more thinning or a bit less thinning, but things on average will even out. And is it really worth chasing that down to the nth degree? On balance, I don't think so. I think on balance, we need to know what the areas are and we need to make sure that the forest stock is there and we monitor that that isn't taking a nosedive. But I think chasing things along supply chains is challenging and counterproductive. But the problem is that if we don't do that, then we can't demonstrate causality. We can't demonstrate that the stuff that is being used here in this plant came from that place and therefore is good. Now, I don't think that matters. I think what matters is the planet. And like I said, if globally we can keep roughly the same amount of stuff and we can still supply this and we have a few BECCS plants, then I think that's okay. But not everyone sees it that way. And I think that there's a huge public trust and confidence issue here around these technologies that will only be addressed if we have that transparency that chases up the supply chain. So what does that mean? What I'm going to suggest is that we have frankly made this all too complicated. And yes, I've spent a lot of the last 10 years, and Alberto spent a lot of the last year, playing games with life cycle assessment and going through endless calculations with very expensive software and lots of numbers in order to prove what the carbon consequences of different options are. But I actually think that yeah, sure, there's the good, there's the bad, and there's the indifferent. But by and large, we know what drives good practice in feedstock production. We can tell which of the plants that are sitting or proposed are actually efficient or inefficient, a good idea or not. And we pretty much know what we should be using the end-use material for. I know that it's an absolute waste of resource to turn it into a supposedly sustainable aviation fuel, because you end up with about 20% of the energy content you started with. But people can fly, so that's okay. You could have used it much more productively to heat people's homes, but that's choice. So I think that we've made it too complicated and we need to take a step back. I like the idea that we have this whole systems approach that chases things all the way through, but I think it'd be an awful lot easier if we just broke it up into 3 big chunks. And we talked about producing feedstock, converting it into something, and using it for something. And if you do that, that's my semi-detached word there, then you actually have an opportunity to shine a bit more light on things for transparency. Because one of the problems I said is that if we look at, let's say, power production in the UK, you've got to go to quite a bit of effort to work out where that wood came from and what it's being used for and how sustainable and how much carbon, etc. But if we were to break down that feedstock production element and at that point say, okay, let's label this stuff, this feedstock, this biomass, with a number that corresponds to what the UK wants in terms of its scope and its carbon, and we say, right, well, that's a low carbon, medium carbon, or high carbon feedstock, then I think we have something practical that we can actually deal with. We have transparency, and I think that would actually bring quite a bit of liquidity into the market. It would break open the invisible transactions that take place at the moment and the vertical integration of forests and producers and agriculturalists with different power plants and fuel suppliers. And I think having a more open market basis whereby the material was traded with an associated carbon figure would actually help a lot in terms of public trust and transparency. I also would argue that wasting time doing lots of calculations, whether it's for purposes of academic papers or for purposes of policy, actually is of limited benefit when you know that there is substantial uncertainty around where the stuff came from in the first place, how it was produced, and what the indirect or otherwise consequences of it were. It just doesn't make sense. We just need a ballpark number for each of these things, for the feedstock, for the conversion efficiency, and for the end bit. So for the feedstock, I think what we can do and should do is identify for different feedstocks what the key non-carbon impacts are. And I think you could set minimum thresholds, and that would do all this stuff on, protecting biodiversity and eutrophication and all the rest of it. So you set that out as minimums, but then you define what your carbon scope is for your system. And I think the UK should do this from the UK's perspective. I'll come back to that if people want later. But we need to define that scope of system for our supply chain, and then we need to quantify the carbon impacts of a particular supply chain and say, okay, that one's big, that one's middle, that one's low, whatever. I don't really care, but I think we need to band the results and trade the products within bands, much the same way as I was just looking the other day. I was thinking of buying a new fridge freezer, and I was realizing that we no longer have A's and A pluses, but now we've gone back to the A to G mechanism for this. But it's the same notion that we have a simple banding that we can recognize roughly equivalent feedstocks on, and then we can waste less time actually chasing all these silly numbers through. Conversion. Now, this one is interesting because the performance of a conversion plant is variable and it's subject to variation. So that's how you've designed it, what it looks like, but also when you build it, it doesn't actually always perform the way you thought it was going to do. Now, I think there's an argument here around innovation in that what the UK should be doing is moving forward with more efficient plants, and we should be encouraging people to take risks, and we should be encouraging people to do things in a more efficient way. And therefore, I think there's a huge argument for saying, look at the planned design and the intent and reward that, not what actual output you get. So that's what I mean when I talk about the carbon reward for this. What you could do then is if you had, in the same way today, Ofgem have the right to go into every plant that claims renewables obligations in the country, and I have done this job in the past, and gather all the data and look at what they're doing and check that it's as they said it was and to check that the numbers are right. So you could then actually gather site-specific data around the different types of technologies and what they're actually performing like in the real world, and that breeds a circle whereby you can then have continuous improvement. So I think we should reward people for taking risks, and we should reward the ambition around the efficiency, but at the same time monitor what they're actually achieving so that we can also improve. And the vector, the far end of it, I think it's very difficult at the moment to argue that we should be continuing to use open combustion of biomass for the electricity sector. And that's because the electricity sector is rapidly decarbonising. And I think we can all see the time coming when the band within which some biomass plants currently sit may no longer be below the threshold of what perhaps a wildly optimistic UK grid average could be, but we can certainly see that in the next 20 years, I think. And so I think we need to be careful about where the sector is that we're actually targeting our biomass. Certainly at the moment, heat would be a very good idea from an economic perspective. But again, from a carbon perspective, does it really make sense? So where we target biomass isn't really determined by what the biomass can do. It's determined by what the best alternative is. And that means that we need to set benchmark performance levels for the sector and how we expect it to move based on our decarbonisation plans for, let's say, the coming 30 years. If you do that, then that allows people to plan. It allows people to look at a plant that they want to build and how they're going to design it and say, actually, we'll feed that into the fuel system, we'll feed that into natural gas, we'll do whatever with it. And it also allows you to reward that performance to allow people to then attempt to build more efficient plants, because at the moment that isn't on most people's radar. It's to play safe and to build something that's bankable and that we've done before. You could also then modify the targets that you have for the different sectors to reflect evolving markets. So we would, for example, at the moment be saying, all right, well, let's put the price up on the heating front because we have a need that has evolved in that area. So I think that we can set those benchmarks, and that does need to be done centrally. I think it can be informed by academic views, but actually it needs to be done by government in view of what it believes the decarbonisation plan and strategy is. Of course, it would help if there were a strategy of that. Anyway, conclusions. Where does this leave me? Can BECCS reduce carbon emissions? Undoubtedly, yes. I really believe that is true. It can. But I think that we need to be careful about maximising cost-effective reductions. And I probably could have said this a month ago, and people would have nodded a bit blithely, but I think today that is really apparent. The carbon reductions are important, but the cost and the affordability is also important. And the ways that we do that to make the best use of biomass are really quite simple. We need to avoid really bad feedstocks. We need to improve the efficiency of the conversion system. So we need to incentivize that and encourage people to go higher and to take risks on that and to try out new engineering areas. And we need to target the reductions that we can achieve with biomass where they are most valuable. So those are my three semi-detached sectors again. I think it is complicated. That's why I like it. That's why Supergen is such a stimulating and exciting place to be. That's why we had lots of early career researchers sitting there next door earlier talking about new challenges and still scratching their heads on how to get their heads around different things. We did a wonderful exercise this afternoon on communications where people were trying to explain what other people did. And I think that sort of brings round, the novelty in this area, that there's always something new and something new happening. So I think it is complex. And I think we therefore need to simplify things. Actually, that's what we were doing in the comms exercise this afternoon. We were simplifying and trying to get to a common denominator. But we've got to do it. Because frankly, we don't really have any other options. So that was from me. It was also from Alberto, whose slides I made heavy use of. It was from Miriam, who did a lot of that work on the Fab GGR and the systems element of Supergen. But if I pulled up the correct version of this presentation, it would also have three other names on it. And it would be, and I'm not sure where they've gone, it would be Emma, Joanna, and where's she gone? Rebecca, taking the photograph at the back, because by them getting on with running Supergen and doing everything, well, Emma running Supergen and doing everything else gives me the time to go and mess around making slides for everybody. Joanna has done an absolutely outstanding job this last year or so, converting a lot of this sort of thinking into mechanisms that are having traction with some of our colleagues in different government departments. And Rebecca is responsible for our engagement with our industrial stakeholders, of whom several are in the room today, and even more will be here tomorrow. So there you go, job done.
question or two.